All right, guys, we're back with our very last lecture for this semester. It's on the second shifting theorem for Laplace transforms. As usual, the prerequisites: you need Laplace transforms, and you really need to have watched the 10.6 lecture on unit step functions, right? So if you don't know how unit step functions work, then some of this notation is not going to make any sense, right? So make sure that you go through and you watch those. So I'll give you a couple definitions to start with. This lecture is not going to be very proof heavy because I'm going to give you a couple definitions that we're going to use, and then I want to go through the normal Laplace transform things. I want to translate something, I want to untranslate something, and then I want to actually work a problem showing you how these things work. Okay, so I'll be very clear on the step-by-step process how you use this. But like all the other things that we do this semester, it takes practice, right? Okay, so your book gives a couple different definitions for the Laplace transform of a piecewise function, but the one we're going to use is this one. The Laplace transform of u sub a of t, right? So this is my unit step function, times f of t. This is equal to e to the negative as times the Laplace transform of f of t plus a. Okay? Okay, sure. Let's see how that works, right? So let's actually work a problem. We'll see how that works. Okay? So I'll pull an example up here. Here we go. Okay, so as by way of an example, let's say f of t is equal to the piecewise function. Here we go. We got 1. That's from 0 to 2, and then e to the negative t minus 2. You know what, we're going to make this now we'll just do 2 minus 2. Okay. I was going to make it a little bit more complicated, but I figure maybe we'll hold off on that. Okay. So I want the Laplace transform of this. So the first thing I have to do, since my Laplace transform is written in terms of this unit step function, is, well, I gotta actually write this down in terms of my unit step function, right? So using what we learned in section 10.6, I have f of t is equal to, so remember this is the left piece, that's the right piece. So this is 1 minus u sub 2 of t times the function 1 plus u sub 2 of t times e to the negative t minus 2. Okay? Now this is not the form I wanted in. I want this grouped together to where all my unit step functions are in the same spot. Okay? So this is 1 minus u sub 2 of t plus u sub 2 of t times e to the negative t minus 2. I'm going to take the u sub 2 of t out of these two terms. And what I get is I get 1 plus u sub 2 of t times e to the negative t minus 2 minus 1. All right, so this is what I'm going to use for f of t, right? This is what I'm going to use for f of t. Okay, fine. Okay. What I would like then is I would like to take the Laplace transform of this, right? So I want the Laplace transform of 1 plus u sub 2 of t times e to the negative t minus 2 minus 1. Okay. All right, I'm going to have to erase this here in a second so to get some more room. But the first thing I'm going to do here is, remember that my Laplace transform, this is a linear transformation, right? So I can actually rewrite this as, well, the Laplace transform of 1 is 1 over s. Okay, so I can rewrite this as 1 over s plus the Laplace transform of u sub 2 of t times e to the negative t minus 2 minus 1. Okay. All right, so now that I have what I'm looking for, I go to my definition. So look at my definition. This exactly fits this as long as the function we're talking about is this function right here. Okay? So, well, what does this tell me to do? It tells me that, now notice the first thing I need is a, u sub a of t, a here is 2, right? Okay? So the first thing I need here is I need to write, here we go. Okay, so I've got 1 over s plus, okay, so I've got e to the negative 2s. Remember, a is 2, u sub a of t, so that's where the 2 comes from, times, this says the Laplace transform of f of t plus a. Now remember, f here in this formula is referring to this function, which is inside of my Laplace transform. And what that's asking is, it's asking us to shift this function left a units. And here, a is 2. Basically, replace all the t's with t plus 2. Okay? So I want the Laplace transform of e to the negative. Instead of t, I'm going to have t plus 2 minus 2 minus 1. There we go. Well, yeah, but that simplifies. Okay? Specifically, t plus 2 minus 2, well, that's just t, so that's e to the negative t minus 1. So this is 1 over s plus e to the negative, negative 2s. The Laplace transform of e to the negative t, that's 1 over s plus 1. And the Laplace transform of 1 is 1 over s. There you go. Okay? So this is the Laplace transform of this piecewise function. Okay? That's not terrible, right? And the only issue you might run into is this was actually kind of nice, right? So the plus 2 and the minus 2 canceled. What would have happened if that wasn't the case? Let me make some adjustments here. Okay. The real question is, what would have happened if this was just, let's say, e to the negative t, right? Well, nothing changes in the structure for the rewriting, right? This is just negative t. That's just negative t. The problem comes in whenever we get down here. That's negative t. Because instead of having plus 2 minus 2, I get this. And the question is then, at this point in time, how do you take the Laplace transform of e to the negative t plus 2, right? Because everything else is going to be the same. Just this is the only term that will end up being different. Okay, and that's actually not that terrible as well. All I have to do is I've got to split that up. So e to the negative t. E to the negative t plus 2. That's e to the negative t minus 2, which is e to the negative t times e to the negative 2. So if I want the Laplace transform of e to the negative t times e to the negative 2, so this term here, okay? Remember, e to the negative 2 is just a constant, right? So this is just the Laplace transform of e to the negative t, that's 1 over s plus 1 times e to the negative 2. Okay? This ends up being a scalar. For exponential functions, they'll always just split this way. For, let's say, sine and cosine functions, you'll need to do some sum and difference formulas. And for polynomial type functions, well, replacing a t with a t plus 2 is just going to lead to, well, a different polynomial, right? if it's t squared and you replace it with t plus 2, now you've got t plus 2 squared, right? So you'll have to expand those things, and it'll create similar terms, right? So just make sure if things don't cancel and don't come out nice, just make sure that you sorry, the completionist in me is making me write this down. Make sure that you expand everything before you actually take your Laplace transform. Okay? All right, so overall, translating, not terrible. Okay, let's untranslate. Okay? So this is going forward, and this leads to a very logical definition for going backward. Okay? Okay? I'm going to rescale it a little bit. So if I rescale this, because I don't want the shifting to be on the front end, I want the shifting to be on the back end. Okay? So the inverse Laplace transform of e to the negative as times remember that f of s is the Laplace transform of f. I don't know what f is, right? So this is e to the negative as times the Laplace transform of something. This is just equal to u sub a of t times, well, I'm going to write this in terms of f. It's just easier. F of t minus a. Okay? So where Laplace transform of f is capital F of s. Okay? Okay. Again, let me go ahead and work an example here. There we go. All right. Yeah, that looks like fun. Okay. So here's my example. Okay, so I want the inverse Laplace transform of, what do I have here? I've got 2 times e to the negative s all over s squared plus 4. Now, I'm going to give you a word of caution here, because I'm not going to work an example where this has to be done. When we invert these Laplace transforms, every now and then we have to do partial fraction decomposition to split these fractions up. If you want to do that, or no, I don't have to do it here, obviously, but if you want to do that, if you end up doing partial fraction decomposition, do not keep this exponential function in your numerator. Factor the e to the negative s to the front and then decompose the other fraction, right? So if I wanted to decompose this, I would want to rewrite it as e to the negative s times 2 over, actually, and I want to decompose that part, right? I don't want to decompose with this. It's not that you can't do it, it's just kind of a pain in the butt, right? And we don't want to do that. It'll lead to, messy things, and it's much easier if you just sort of pull it out first and then distribute it back in. Okay, so now I don't need it here, okay? I don't need it here because, okay, when I rewrite this, same form, I notice that this is the Laplace transform of sine 2t, isn't it? Yeah? Laplace transform of sine of bt is b over s squared plus b squared if b is 2. Laplace transform of sine of 2t is 2 over s squared plus 2 squared, right? So this is Laplace transform. So if I rewrite them, I rewrite this according to exactly my formula here. Okay? This is the inverse Laplace transform of e to the negative s times the Laplace transform of sine of 2t, right? So now this matches this formula exactly, right? F of s is Laplace transform of this, okay? So if I look at what it tells me that this should be equal to Okay? U sub a of t. Well, what's a? To get a, of course, we look at here, e to the negative as. Here, a is 1. Okay? A is 1. So negative as, this is negative 1s, a is 1. So this is u sub 1 of t times, okay, so remember that this function is the Laplace transform of f that I'm looking for. So here's f of t, right? So by my definition, that's f of t. And what I want to write is f of t minus a. A was what? It was 1, right? So I want to write sine of two t minus 1. Okay? Just replace t with t minus a. Okay? And there's my inverse Laplace transform, right? Yeah. And again, this is a piecewise function. The important thing that we're doing with these things is that this second shifting theorem handles piecewise functions really, really well, right? So again, this is a function that's 0 until you get to 1. And then as soon as you get to 1, now it looks like this sine function, right? Okay. All right, let's see if we can't utilize these methods, maybe solving a problem, right? Solving a... Well, sort of put everything together in sort of one culminating problem here. All right, let me see. Okay. So I've got good Lord, give me something fun. All right, we'll do that one. Y prime plus 2y is equal to f of t, where f of t is defined as, okay, f of t is, it's 0 or sine of 2t, okay, and it's 0 as long as t is between 0 and pi, and then it's sine 2t as soon as t is bigger than pi, right? And I'm given one more thing. I'm given an initial condition here. Remember, you always have to have these initial conditions to solve, because when I take the Laplace transform with that derivative, I'm going to require those initial conditions, right? Okay. So let's see if we can do this. So the first thing I want to do, I need to rewrite f of t in its unit step notation, right? So let me rewrite that first. I've got y prime plus 2y. So this is going to be, well, I've got 0 on my left-hand step, so that's nothing. And my right-hand function, that's just u sub pi of t, remember it turns on at pi, times sine 2t. Okay. All right, now let's take a Laplace transform. Okay, so I want to take the Laplace transform of y prime plus 2 times Laplace transform of y. That's equal to the Laplace transform of u sub pi of t times sine 2t. Okay. All right, so Laplace transform of y prime. So we remember this from the from our function video 10.4. Okay, this is s times the Laplace transform of y minus y of 0. Okay, so again, Laplace transform of y prime gets replaced with this term. Okay. So now I've got plus 2 times Laplace transform of y. Okay? And then the right-hand side is where my unit step function comes in. So I remember my drop the cap. My definition here, this is, so A is pi, so this becomes e to the negative pi s times the Laplace transform of f of t plus a. So this is the Laplace transform of sine of 2t plus pi. Okay? Well, what is the Laplace transform of sine of t plus pi? Well, let's do some scratch work. Okay? So I'll do some scratch work up here on the right, and then I'll have to erase it later. So the Laplace transform of sine of 2t plus pi. Well, that's the Laplace transform of sine of 2t plus 2 pi. Well, now wait a minute. Isn't the period of sine 2 pi? So shouldn't that be equivalent to sine of 2t? Okay. If you want to use the angle sum definition, we can do that. Using my angle sum definition, this is the Laplace transform of sine 2t cosine 2 pi plus sine 2 pi cosine 2t, right? But cosine of 2 pi is 1, so that's sine 2t times 1. And sine of 2 pi is 0, so 0 times cosine of pi. Yeah, so I get away with having a really nice Laplace transform here because this is just 2 over s squared plus 4. All right, fantastic. Let's go back down here and we'll rewrite some of these things. I have no idea why I keep dropping markers today. This is ridiculous. Okay, so y of 0 is 3. So I'll write s times Laplace transform of y plus 2 times the Laplace transform of y is equal to, here we go, over here I've got 2 e to the negative pi s over s squared plus 4 plus 3. That negative 3 here is added over to the right. Okay. From this point, I can factor out the Laplace transform of y. Now I've got the Laplace transform of y times s plus 2 is equal to 2e to the negative pi s over s squared plus 4 plus 3. Okay. Now, you theoretically could combine these two terms, but don't, because clearly this one's going to be a second shifting theorem and that one's not, right? So I'd like to keep those things as separate as I can for as long as I can. At this point, I'll divide all of my terms by s plus 2, and that gets me to the point where I need to start untranslating things. So divide everything by s plus 2 gives me that the Laplace transform of y is equal to 2 times e to the negative pi s over s squared plus 4 times s plus 2 plus 3 over s plus 2. And again, dividing everything by s plus 2. So now I just need to untranslate this, right? Untranslating this statement right here will give me the function y I'm looking for. Fantastic. That is done in two parts. One part which does not use the second shifting theorem, and one part that does. That term on the right, that does not use the second shifting theorem, right? Okay, we can untranslate 3 over s plus 2 pretty easily. Okay, so let me write r. So what I have here, I have that y is equal to, okay, the inverse translation for 3 over s plus 2 is 3 e to the negative 2t. Okay, so plus, here's what I need to put some effort into, the inverse Laplace transform of e to the negative pi s times 2 over s squared plus 4 s plus 2. Okay, now, okay, for this, I need to use partial fraction decomposition to break this apart, right? So I'll break that apart. I'll use partial fraction decomposition. Okay. Let me go ahead and do that. All right, so again, some scratch work. I've got 2 over s squared plus 4 times s plus 2. That's equal to as plus b over s squared plus 4 plus c over s plus 2. Rewriting this, I get 2 equals as times s plus 2 plus b times s plus 2 plus c times s squared plus 4, just multiplying through by my common denominator. Okay. Again, I can get at least one cheap value here, considering s is equal to -2. The left-hand side gives me 2. These two terms will both die because -2 plus 2 is 0. But over here, I get c times -2 squared plus 4. That's c times 8. c is equal to 1/4. Okay, fair enough. How to find a and b? Well, again, notice that a has an s attached and b doesn't. So I'm going to go ahead and look at the largest degree terms over here on the right. Those are the quadratic terms. If I look at my s squared terms, on the left-hand side, I don't have any. That's 0s squared. On the right-hand side, I've got as squared plus, well, b doesn't make any s squared terms, right? b times s, b times 2. But I do have a c times s squared. That gives me 0 is equal to a plus c, but c is 1/4. So a is equal to -1/4. All right, almost home free. Again, I went to the highest degree term. Let me go to the lowest degree term. That's the constant terms. I know a won't participate in any of those because it has an s attached. Okay, so if I look at my constant terms, okay, on the left-hand side I've got 2. On the right-hand side, again, a can't make a constant term, right? It's as squared plus 2as, but b can, so that's 2b plus c times 4 plus 4c. But again, I know c is 1/4, right? So this is 2 equals 2b plus 1. This gives me b is equal to 1/2. Okay. All right, so I have my decomposition, right? I now know a little bit more about what I want to decompose. Okay. So y is e to the 3 times e to the -2t plus the inverse Laplace transform e to the negative pi s. Okay. So I've got a, where's a? So -1/4 s plus b, so plus 1/2 over s squared plus 4 plus, see, here we go, 1/4 over s plus 2. Now, I'd like to factor out a -1/4 from all these things. The reason I want to do that is I'd like to make these coefficients in my numerator a little bit nicer, right? Yeah, so let me go ahead and do that. Okay, if I factor out a -1/4, I get 3 e to the -2t plus the inverse Laplace transform. So I'm going to have -1/4 e to the negative pi s. Okay, really I could take the -1/4 all the way out of this Laplace transform, considering it's a scalar, but that's fine. Okay, so I take out a -1/4. I'm left with s minus 2 over s squared plus 4. That's really nice. Plus, well, I already wrote the plus. -1 over s plus 2. Okay. I think if I rewrite this one more time, I can get us to where we're going. So remember, this is now a sine and a cosine, right? Yeah. I know it's s squared plus b squared, so I know it's going to be trig functions, sine and cosine. Cosine is s over s squared plus 4. So b would be 2 if that's b squared. Sine would be 2, so nice for us that we have a 2. Sine would be 2 over s squared plus 4. So I think if we rewrite this, here we go, that's 3 times e to the negative 2t plus the inverse Laplace transform of negative 1/4 e to the negative pi s times, we're going to go with s over s squared plus 4 minus 2 over s squared plus 4 minus 1 over s plus 2. Okay. All right, so we're almost there, right? We're almost there, okay? Now, to untranslate, what I need to do is I need to untranslate this part, yes? And then I'm going to need to shift it back pi units, right? Yeah? So let me write the untranslation for this. Here we go. Okay. So that right there, that is the Laplace transform of, that's cosine 2t minus sine 2t minus e to the negative 2t, right? And my second shifting theorem, the inversion part of my second shifting theorem, tells me that what I want is I want to shift these things back to the right a units, right? So I don't want f of t, that's what f of t is. I want f of t minus a, right? So I want f of t minus a. So let's see if I can't write this up here. Okay. So I've got y is equal to 3 e to the negative 2t plus, okay, so, well, I should write minus 1/4. Pull that out. Okay. So e to the negative pi s, that's going to give me a is pi, and if a is pi, then I'm going to have a u sub pi of t right here. Okay? And now I just need to write these things shifted to the left, pi units. Okay? So that's going to be cosine of 2t minus pi minus sine 2t minus pi minus e to the negative 2 t minus pi. Okay? Now, technically speaking, we could be done. I mean, this is a solution for y, but that seems like a very unsatisfactory way to write this. It's not really simplified, right? Because, again, I could rewrite those trig functions that's cosine of 2t minus 2 pi, and then sine of 2t minus 2 pi. There's nothing I can do about this. That's just ugly. Okay. Oh, I can write it correctly. I can certainly do that. Okay. But again, the period for cosine and sine is 2 pi. So cosine of 2t minus 2 pi is just cosine of 2t. So in the end, this is the function y we were looking for. Yeah. So y is equal to 3 e to the negative 2t minus 1/4 u sub pi of t all times cosine of 2t minus sine 2t minus e to the negative 2t minus pi. Fantastic. Okay. Yes, I know what you're thinking. Are they all going to be this fun? Yes. Yes, they are. Okay. But they do get easier with practice, relatively. They get relatively easier with practice. Okay. Just make sure that you're doing the best you can. Do your homework. Now, Again, this is the last material for this course. Homework's already been posted. Please make sure you're getting that done as soon as you can, and email me with any questions. All right, guys.